Uh, our first speaker is Professor Tim Maudlin. Needless to be introduced further, one of the pioneers of foundations of physics and philosophy. Professor Maudlin is an American philosopher of science and professor of philosophy at the Department of Philosophy of the University of New York. Professor Maudlin interest has primarily focused on the foundations of physics, metaphysics, and logic. He published many papers in foundations of physics, metaphysics, and philosophy of science. Moreover, he published several books such as Quantum Non-Locality and Relativity, Metaphysical Intimations of Modern Science, The Metaphysics Within Physics and Philosophy of Physics. Today, Professor Maudlin will be talking about prospects for superluminal information transfer using quantum non-locality. It is an honor that you accepted our invitation, Professor Maudlin, and we are looking forward to your talk. You can start your speech.
Okay, thank you very much, and thank you for inviting me. I'm not sure if I can control the slides right now, because before they figured out a way that they could transfer the control of the slides to me.
Okay, Professor Maudlin, you must click on the three dots icon and.
Oh, right. Okay. Okay, there it is. Take ownership. All right, got it. Hopefully that'll work. Let me just check. All right, I've got that, but I don't seem to have control. Oh, down here, right. Got it. Good. So thank you very much for inviting me. I, obviously couldn't follow the earlier talks for linguistic reasons, although I could see the slides and, the title. So I think I have some idea of what people have been talking about. I'm going to give a talk. This is the first time I've ever given this talk, and it's about material that really isn't my own. But I think it's extremely intriguing and extremely interesting. And I think that one way or another, although one can't quite predict how, we'll learn a lot by thinking through the following issue and the following actually experimental suggestion, which may has a chance of being carried out. One thing that I find very exciting about this particular topic is that often issues in the foundations of physics don't seem to have any immediate implications for experiments. And this does, as you can imagine, just given my title. So I just want to set it up. Actually, the technical part of this, or the result that runs it, is very easy and it'll go very quickly. So there's just a lot of setting up, and then very quickly I'm going to give you some an overview of some results. And again, these are not my results at all. So what we know is that quantum mechanics predicts, and more importantly, actually there appears in the laboratory, violations of Bell's inequality for experiments done at space-like separation. And the lesson to be learned from that, according to Bell and according to me, although it's been decades and decades and decades of argument, is that since the inequality is derivable essentially from a postulate of local causality that Bell writes down, if you violate the inequality, it just shows that the world is not locally causal, in the sense that not all of the causal influences on an event have to lie in or on its past light cone, right? So in a locally causal theory, the simple way to think about it is that anything that could have a causal impact on an event must be either in or on its past light cone, and it follows immediately as a corollary that any effect that an event has must lie in or on its future light cone. That is a feature of Maxwellian electrodynamics. that is a feature of the general theory of relativity. So classically, both electromagnetism and gravity could be formulated in ways that were clearly causally local. And because of that, those theories could not predict violations of Bell's inequality for space-like separated experiments. Now, Bell realized that quantum theory did predict such violations. Clauser, Aspey, and Zeilinger, with more and more detail, more and more safeguards, and better data, keep showing that, in fact, the quantum mechanical predictions are correct here, and you can violate the inequality for these separated experiments. So what follows? Well, I claim what follows is the world is not causally local. And if Alice and Bob are in their labs very, very, very far away from each other and doing things at space-like separation, nonetheless, something that happens in Bob's lab can influence the outcome in Alice's or vice versa. It must be so. And that is exactly the thing Einstein didn't like about quantum theory, that spooky action at a distance, but it looks like this phenomena cannot be accounted for without it. Now, once you accept that, and again, it's a big struggle to get people to accept that for reasons we'll come up in a second, something that immediately occurs to you, and this is when I say it's merely a suggestion, I mean, it's not a theorem, obviously, but it is something that would occur to you, which is, well, if something going on in Bob's lab can affect the outcome in Alice's or vice versa, then it seems likely there would be some way to use that, to harness it in order to send signals between the two labs. That obviously doesn't immediately follow that you can do that, but you sort of suspect you ought to be able to, because you're saying that there really is a dependency of the physical occurrences in the one lab on what's going on in the other lab. And you would think, well, why can't I somehow arrange things so that that dependency allows for signaling? Well, what does one mean by signaling? Now you've got to bring in a concept that is a slightly new one. Fortunately, Shannon already did us the service of giving us a nice technical, formal account of signaling. We assume in order for Alice to signal to Bob, she has to be able to do something which at least slightly changes the chances of certain things happening that Bob can detect, that Bob can actually see. So you need a manipulable part on Alice's side and an observable part on Bob's. Now, it could be that you have superluminal causation, but there's just something that prevents you from using it in this way. If that's true, then we still have an interesting question, which is, what is it that's preventing it? I mean, we would like an explanation. It doesn't seem sufficient, for example, to merely check some proposed schemes and then notice on careful checking that they don't work. One would think there must be some articulable general reason why no such scheme could possibly work. And so there are two possible outcomes here. Is one might find such a principle and at least grant that you can't superluminally signal, but have a sense of why you can't. Or if someone offers such a principle, it might also provide a target for thinking of ways around it, that there may be a reason why many of these schemes don't work, but it's not a surefire reason why none of them can work. And it would actually give you guidance to try and find a scheme that would work. What I want to do just to set this up, and again, the actual content of this is going to go very, very, very quickly, is just set up an analogy, because I think many people here will be familiar with this, and that's arises when thermodynamic principles, which had been developed in a fairly independent basis, get absorbed into or explained by the kinetic theory of heat and the molecular theory of matter. So you already had an up and running science of thermodynamics that was independent of having accepted either the atomic theory or the kinetic theory of heat. And once the kinetic theory was accepted and you said, well, really what heat is nothing but the mean kinetic energy. It's the kind of disordered kinetic energy of a bunch of particles or a bunch of parts of a very large system. One immediately asks, all right, so really heat is kinetic energy. Well, why can't I tap into that and somehow recover some of that disordered kinetic energy in a more ordered way as useful mechanical work? And that's really the fundamental question of thermodynamics as it was originally formulated, was I've got heat energy and I would like to convert it into mechanical energy and make engines run and cars go and so on. Well, how can I do that and how efficiently can I do that? And we know Carnot and so on made lots of progress on some general principles of heat engines. But if you just sit down and do a simple calculation about how much energy there is in heat in, say, the ocean, of course, the number is just going to be unimaginable if you just add up all the kinetic energies of all the particles in the ocean. And so it would occur to you that if there's some way to just convert that, even without a lot of efficiency, into useful mechanical energy, then with the effect of cooling the ocean a little bit, right? You're not violating conservation of energy, you're just moving the energy around in a certain kind of way. If you could do that, then you would have a device of tremendous practical use. Now, Maxwell understood all this, and the whole point of his example of the demon was to say that various accepted thermodynamic principles or thermodynamic laws, once you understood them in the context of the kinetic theory of heat and statistical considerations, could in principle be violated. That there's nothing in the physics itself that would stand in the way of doing what I just said. That is, taking the heat energy in a system and converting it into mechanical energy. An easy way to see that is if you had a body of gas or a body of liquid at a constant temperature, say like the ocean, and you wanted to somehow get mechanical energy out of it, one thing you notice is if you could just manage to create a temperature differential, if you could somehow get a difference in the temperatures in two regions of this thing, which is initially at equilibrium, so the temperature is not uneven, then you could run a Carnot cycle between those two parts, and you know how to extract energy, how to extract mechanical energy out of a Carnot engine. So then the question comes up, well, could you somehow manage to induce a temporal differential in your body at equilibrium without an energy cost to doing that? Now, one of the principles of people often say that what Maxwell was dealing with his example of the demon is the second law of thermodynamics. That's really, I don't think, quite correct. What he was dealing with was another principle, which was an accepted principle of thermodynamics, which was that if you have a body that's come to equilibrium in its temperature, that you can't induce a temperature gradient in it without doing work on it, right? So you have to put energy in order to get a temperature gradient. And then, of course, you might be able to use that temperature gradient to run a Carnot engine. But then the question is, can you get as much energy back again as you put in? And the answer generally is going to be no, that you're going to put some energy in to create the gradient, then you're going to run the engine. And at the end of the day, the entire thing will be back at equilibrium at a higher temperature because you had to put some net energy into it. And so you're really not making any progress by this. But what Maxwell realized, and it seems perfectly correct, is that if the kinetic theory of heat is right, then the demon, who, remember, just can see of a particular molecule what its motion is at the moment, right? How much energy it has and what direction it's going in, that the demon can then open and close little doors and either allow that particle to pass from one side to the gas to the other or not. And the point is that in doing so, the demon performs no work on the gas, right? The demon doesn't push the gas around at all. If he opens the door, then the particle just sails through and no work is done on it. And if he closes the door, then it just elastically bounces off, and again, no work is done on it. So all of this door opening and closing that the demon engages in is not doing work. Nonetheless, it will actually create a temperature differential where there originally wasn't one. And having done that, you could then set up a Carnot engine and extract some work out of your gas, and the total temperature at the end of that, the thing would be back in equilibrium at a lower temperature. Okay, so what Maxwell is pointing out is that this thing that was considered to be a thermodynamic law, that you can't induce a temperature differential without doing work, isn't really a law. It can be violated. There's nothing in the fundamental nature of physics that would stand in the way of violating it. So why can't we do it? I mean, that immediately raises the question, since it would be a nice practical thing if we could actually do that. How can we do it? Now, Maxwell's view was that the only reason we can't do what the demon can do, is because we're too big and we're too clumsy, and our perception is not acute enough to actually pick out the individual atoms, and our fingers aren't small enough and quick enough to open and close the individual doors. And that's just a practical limitation, right? So all we can do is deal with these collections of atoms en masse, right? I can take a whole bunch of them and put a piston in and push them all together, but I can't do something that will differentially react to one atom and not to another. But if you could, then you could get around this principle of thermodynamics. And so what Maxwell says is that the laws of thermodynamics, and this then would also include the second law, are not really ironclad laws. They're just statistical regularities. They're the consequence of probabilistic considerations if you can only act in this very gross way on the system. That led people to say, well, but maybe we can be cleverer, right? Maybe I can construct, maybe I don't have to just, I can do more to a gas than just push it with a piston or stick it against a thermal reservoir. Maybe if I'm clever, I can figure out a way to interact with the gas and in fact extract usable mechanical energy out of it. Now, various schemes of this were proposed. For all I know, they're still being proposed. On closer analysis, it tended to be that you would see they wouldn't work. And a famous example of this is Richard Feynman goes through in some detail the idea that because in a gas, you're going to have statistical fluctuations, you could set up a system that would be randomly pushed to the right and left by these statistical fluctuations. And then you use a ratchet and pawl mechanism to, as it were, capture the motion only in one direction. The ratchet and pawl would, as it were, allow something to turn this way, but not to turn back. And then just by the random fluctuations, you would accumulate motion in one direction, and you could use that to lift a weight or something like that. And Feynman then goes through in great detail why, on closer analysis of the thermodynamics of the ratchet and Paul mechanism, he says this really can't work. And that's perfectly fine for that particular example. But again, someone might say, all right, well, that didn't work. Let's try something else. So what you want is a principle. You want some general thing that might already tell you before you start that these schemes aren't gonna work out. And eventually people settled on the idea that that's really Liouville's theorem. So now you're doing something quite precise. You're saying, let's now assume that the microdynamics is governed by a Hamiltonian, and it's, you know, a classical kind of dynamics, and that because it's a classical dynamics, it's going to satisfy Liouville's theorem. And then therefore, and I've got question mark, exclamation, question mark, because the big issue is what you mean by therefore. It somehow follows from Liouville's theorem that no such scheme can work, or that no scheme for causing entropy to go down can work. Now that raises, again, lots of questions. If you want to try and think, can I still get around this problem? The arguments have a bunch of different lemmas, and you could question each one, right? You could question whether Liouville's theorem really does follow from the Hamiltonian dynamics, right? You could question whether the actual microphysics of a real physical object is governed by a Hamiltonian dynamics. The answer to that, of course, we now know is no, because of quantum mechanics. It means that one, in principle, ought to revisit this whole thing from a quantum mechanical perspective. And there's another question, which is, well, even if I grant you that the microdynamics is Hamiltonian and it does always satisfy Liouville's theorem, does it really follow from that you can't do the thing that you're trying to do? And the reason why I wanted to go through all of this setup was that many of you will know that David Albert, in his book Time and Chance, gives an argument that, in fact, you can get around the result, not by violating the theorem. Sorry. Sorry about the dog. Not by saying that Liouville's theorem doesn't hold, but by saying, no, it really doesn't follow, just because Liouville's theorem holds, that you can't, in fact, have a device that would systematically and predictably cause in his case, the entropy of a large system, isolated system, to go down. Now, I don't want to, at this point, right, one thing that I would do if people weren't familiar with David's argument is to try and lay out David's argument and see what kinds of problems may arise for it, but that would take us off of our subject matter. I just want to present this as a kind of analog here. Whatever you think of David's argument, in the end, he's raising a good question, right? He's sort of saying, all right, I'm gonna grant you a bunch of stuff and still ask whether what you think follows from that really does follow. Maybe I can set up a situation where you'll see it wouldn't follow. And the other point about it is, if you look at what David does, again, whether you think it works or not, it's not a practical device, right? It's not a device that, yeah, you just stick this in the ocean and you get a lot of electricity coming out, and the ocean gets colder, which is sort of what you would hope. I mean, it's kind of a fantastically huge, monstrous possible device that could never actually be practically implemented, and even if it were, would only yield a tiny, tiny, tiny gain of energy or lowering of entropy if you could do it. But so what, right? I mean, our question here is not the practical one of how, at what scale you could do this. It's the theoretical one of, can it be done at all, to any degree? And David suggests that, in fact, it can be done to some degree, to a small amount. That's the picture I want. That's the kind of attitude I want everyone to be taking here. So we have a parallel question, which I already raised. Is there some way to make use of the non-locality, which has to be the causal non-locality, which has to be in quantum mechanics, and harness it to, in even the tiniest amount, send signals faster than light? Now, again, you asked that in an abstract way, and if you thought there were a general answer, then you would need an abstract general principle that would rule it out. And people have thought there are such kind of abstract general answers. If you don't have that, then you have to start looking at least at individual proposals for doing this and trying to figure out whether they would work or not. And then if they repeatedly fail, try and figure out if there's some general reason why they keep failing. Now, many people believe that we already are in control of the general argument that you can't do this. And there are two things that people will cite. In my experience, there is a theorem that John Bell proved that got later the kind of funny name, the Nobel telephone theorem. And there is a technical requirement in quantum field theory that the field operators that are used, the Hermitian operators that are used to represent the fields, if the positions of the fields are at space-like separation, those operators are required to commute. And this is just laid down as a fundamental principle in formulating the theory. The question is, all right, even if we grant that, does the thing follow from it? And I want to claim, well, it certainly doesn't obviously follow from it, not as a general fact. And the easy way to see this is to actually look at what, at least for Bell's proof, is to look what Bell said about his own proof. Right, so overall, my argument is, as far as I know, we don't have a general proof that this can't be done. And that in addition, we actually have a concrete proposal now for how it might be done. And this is the really surprising thing. Now, there are lots of issues with this proposal. There are lots of objections people could make, and people are making, and discussions going on. But this is a new discussion. I mean, the thing exciting to me about this is that this is just an issue that, as far as I know, has not been discussed. And certainly this proposal has not been discussed because it's pretty new. It's within the last few years. The actual concrete proposal for how you might be able to do this is based on some work that is being done by Siddhant Das and some of his collaborators. And I will give you a reference at the end to a paper that Siddhant and Detlef Dur have published, which is relevant to this. But I should say at the beginning, right, don't blame Siddhant for this lecture, right? It's not him giving it. It's me giving it, and these are my opinions on the thing. And if they're all wrong, right, don't blame him about it. Good. So let me start with the Nobel telephone theorem and what Bell himself says about it. So if you're interested in this, you need to go to his paper, The Theory of Local Beables, and look up section 7, which is called Messages. And this is after he's proven his theorem and he's given these constraints for locally causal theories and noted that the constraints are broken by the predictions of quantum mechanics, and also the experiments seem to show that they're broken. And so he concludes, as I do, that the world must have some non-locality, real physical non-locality in it. But he knows there are people who just want to resist that conclusion. And one way they resist it is by saying, I don't like your definition of locality, or I don't like your definition of local causality. And they try to implement a different definition, one that actually makes use of signaling as part of the definition itself. And now I just want to read to you what Bell says. And this is just the first couple paragraphs of that section. So Bell says, suppose we're finally obliged, which I think we are, to accept the existence of these correlations at long range and the gross non-locality of nature in the sense of this analysis, that is, in the sense of his definition of locality. Can we then signal faster than light? To answer this, we need at least a schematic theory of what we can do, a fragment of a theory of human beings. Suppose that we can control variables like A and B above, those are the settings of the apparatus, like Stern-Gerlach apparatus or polarizer. But we cannot control those like capital A and capital B, which represent the outcomes of the experiments. I don't quite know what like means here, but suppose that the beables somehow fall into two classes, controllables and uncontrollables. The latter, the uncontrollables, are of no use for sending signals, but can be used for reception, right? So suppose there's something you can't control, but nonetheless you can see it. So you could use that for the receiver, and then the sender needs something they can control. And what you want is that by manipulating the part the sender can control, you make a difference to what the receiver sees. Now, Bell then implements this idea in a technical way. He says, suppose that to A, again, this is the observable part, corresponds a quantum mechanical observable, an operator A. Then if dA dB is not zero, that is, if a little change in B, a little change in the controllable thing will lead to at least a little change in the observable thing, we could signal between corresponding space-time regions using a change in B to induce a change in the expectation value of A or of some function of A. Suppose next, right, that what we do when we change B, the thing we can control, is change the quantum mechanical Hamiltonian H, say by changing some external field, so that, and he gives you the equation, the change in H on the left is a certain function of the change in the controllable B multiplied by this operator B, where B, the operator B, is again an observable, that is an operator localized in region 2 of B, right? Localized in the lab of the person who's twisting the knob. Now, what Bell then says is under these assumptions, and again, what are the assumptions? That what can be observed is represented by an operator, and what can be controlled is also represented by a local piece of the Hamiltonian. Operator there too. So Bell then says, well, under those conditions, and now we can bring in this requirement that observables at space-like separation have to commute. Under that condition, then you can prove that in fact, dA dB is going to be zero, so manipulating B can't cause any change in the observable A, right? Now, the thing I want to point out here is, of course, that's Bell's theorem, and part of Bell's theorem, a piece of it, but not all of it, appeals to this requirement that operators at space-like separation have to commute. But the point is that there's all the other parts that go into the theorem, right? There are a bunch of assumptions that go into the theorem. And if those assumptions turn out not to be generally true, then that suggests there might be ways to get around this theorem. Well, what assumptions are there? The central presupposition, I think, that we're going to look at is that every observable characteristic of a system, that is everything that Bob could possibly see, corresponds to a Hermitian operator. If you don't have that supposition, then at least the argument that Bell gives does not go through. And of course, if there were things that were observable characteristics that are not correlated to any Hermitian operator, equally, this requirement that all the operators at space-like separation commute isn't going to get any grip on this situation, because you're saying, yeah, but I'm observing something that is not representable by a Hermitian operator. So the fact that they all commute, that's not going to tell me anything about this other thing that I can see. Well, what could that be? There are things that we know and we've known forever are not in any obvious way associated with Hermitian operators in the standard quantum mechanical formalism. So among these are arrival times. So it's a kind of commonly accepted fact that there is no time operator, right? There's no Hermitian operator in quantum theory that corresponds to how much time has passed or what time is it. And similarly, there's no operator that corresponds to a transit time operator. So you say, well, imagine I have a particle, it starts out here, it's going to end up over there, maybe on the other side of a potential barrier, who knows? What is the dwell time, or how long is it going to take to get from here to here? Or how long does it spend inside this barrier or something like that? Well, there's no operator that'll give you that information. But of course, there are experiments you can do that seem relevant to it, right? If I can release the particle at a certain moment and then time when it reaches some later thing, it looks like I've got data that I can call a transit time. But I don't have any obvious way by using the normal means of making a prediction about that out of the theory. Now, this is a long thing and I'm running a little late, so I won't read it, but I will just say what's in it. This is a passage, this was just given to me last night by Sidhan. I didn't know about this, from a book by Peter Holland on Bohmian mechanics and making exactly this point. And I'll just, you can see at the top, time of transit, a testable prediction beyond quantum mechanics. And he's just making the same point. Everybody agrees there's no time operator. In Bohmian mechanics, in a pilot wave theory, there are just facts about how long it takes a particle to get from A to B. And you have the resources to make calculations about what that ought to be. But standard quantum mechanics doesn't even have an obvious way to make predictions about that. So this might be a place where the pilot wave theory doesn't exactly contradict standard quantum mechanics, but extends it. It allows you to deal with situations where it's not obvious how they go in standard quantum theory. That it's a long quote, and I won't read the whole thing, but again, this is not a novel idea. The new thing now, I mean, I'll just read at the end of it. I can go back. So the last paragraph, we present this as a possibility to explore. In attributing definite times to events, the causal interpretation does not start from or require connection with a time operator. The implication is that the historical problem of time in quantum theory may have been artificially created by the demand that all physical observables be associated with self-adjoint operators. It's therefore possible that the quantum theory of measurement should be modified to include a treatment of observables not directly connected with such operators. But we shall not pursue this line of inquiry. But you can see how exactly that assumption sits at the center of Bell's Nobel telephone proof. All right, so let's think about arrival times. And let's just think about them in a very concrete experimental way. I start with a single particle, and I'm just going to use the common locution here. I have a single electron in a trap, right, in a magnetic trap. This is what anybody would say. We now have the ability to catch an electron and hold it. And then at some specified moment, we just open the trap. If the trap is a magnetic containment, we just open at least one side of it and allow the particle, as we would say, to escape and go down a waveguide toward a screen, where eventually there will be a mark or a flash will occur. It's probably better for it to be some kind of photo effect, right? A flash occurs on the screen. And now we time the moment when we drop the wall and the moment when the flash occurs to as much detail, to as much accuracy as we can. And we repeat the experiment over and over. We don't expect that time difference to always be the same. We repeat the experiment over and over, and we'll get an arrival time distribution. That is just data. right? That's something the world is going to provide us. If we do this experiment, it'll provide us with some data. Question, how do we predict that data using standard quantum mechanics? Answer, it's not clear because we don't have an operator that corresponds to the thing we seem to have observed. So at least the standard way of approaching that question won't work. However, in a pilot wave theory, you can do something else, right? Well, notice not only do we not know how to make the prediction in standard quantum theory, we don't even exactly, or standard quantum theory would object to my description of the situation, right? Because my description was there is a particle that starts out in this trap, and I open the door or I let down the field, and the particle moves down the waveguide and eventually hits the screen. And I want to know what's the time gap between dropping this and hitting. Of course, in standard quantum theory, there is no particle. It's not in a particular place. It doesn't move with a particular rate. It doesn't arrive anywhere. In quantum field theory, people would insist that there are, particles are not fundamental. It's just fields that are doing something. So not only, in the standard approach, you sort of get no help at all about how to approach this question by thinking physically, at least directly, given their ontology. But in the pilot wave theory, the ontology tells you exactly what's going to happen, right? You do have a particle, and it does travel from here to there, and it arrives at the screen at a certain time. And you have the ability, given the theory, to do some calculations. Now, in Bohmian mechanics, we know how to do this. I know other people have talked about this. I assume it's familiar. We've got the Schrodinger equation for the wave function, but then we also have the guidance equation, which tells us how the particles move. Maybe what's not so wasn't familiar to me, is how this is affected by the presence of spin. And this is what Siddhant has been working on and coming up with results that to me were rather shocking, right? As far as I know, no one's questioning these results. So it turns out, if you have a spin half particle, not a spinless particle, but if you have a spin half particle, and you do this, you capture it and then let it move down this waveguide to a screen, that the spin part induces a piece of the guidance equation. The particle will move differently than it would if it were spinless. And to pick this up, you now have to use ideally the Dirac equation, or at least the Pauli equation, to put the spin part in, and the spin part then generates a piece to the guidance equation, a spin-controlled piece. And it makes really quite a difference to the trajectory down this waveguide. Well, what makes a difference? You start with the particle with the spin polarized in some direction. And we're only going to look at the two extreme cases. It could be polarized along the direction of the waveguide. Imagine the waveguide is going this way. It can be polarized along the direction of the waveguide or orthogonal to it. Of course, it could be anywhere in between, but these will give us the biggest contrast. It turns out that according to Siddhant's calculations, when the spin is parallel, what happens? Well, the spin term makes what the particle wants to do is essentially actually orbit around the axis of spin. So a typical trajectory, we imagine the particles moving down the waveguide, and you see it's just following a kind of helix, because the spin, and it doesn't matter whether it's spin up or spin down, the spin is oriented this way and the particle tends to rotate, right? Whether it's spin up or spin down might determine whether it's right-handed or left-handed, but either way you get a kind of helical motion. And it will go at a fairly constant rate down the waveguide. Of course, there'll be an initial distribution, as it were, of different momenta, so that different particles can go down the waveguide at different rates, but they'll just kind of go monotonically down while spinning. But what if I set up the spin orthogonal to the direction of motion? So again, the spin part makes it want to rotate around that axis, but now the motion's that way. And essentially, we get what we get in Ptolemaic astronomy, right? We get retrograde motion. We get a backflow in the quantum flux. And So the particle is going to go kind of quickly forward and then stop and then go back and then go quickly forward. And so you get this kind of motion with orthogonal spin. Now, you can ask, if I have a distribution of particles, all of whose spins are aligned this way, and a distribution of particles, all of whose spins are aligned this way, and I let them go, what will the distribution be for first arrival times? What will be the distribution for when these particles first hit a plane? Right now, I'm just going to do it for a mathematical plane. I'm not going to put anything physical in. I'm just going to indicate a plane and say, when will that trajectory first hit that plane? Now, this is something that can be calculated because you can calculate these trajectories and you know the distributions and so on. And so it's actually accessible to do this calculation. And the arrival time distributions in those two conditions are quite different. This is what, to me was shocking. And this is the relevant data. This is from the paper. I'll give you the reference at the end that Sidhan and Detlef wrote that's published. And the main thing is just to look at the red and the blue curves. Those are the distributions of first arrival time. The blue curve is the case where the spin is in the direction of the waveguide, so you have this helical motion. And that distribution arises because there's a distribution, as it were, of initial momenta, right? Some of the particles, as it were, come out of the box faster and some slower, and then they make their way down, winding like this. And you can see there's a very long tail that goes out. You get very, very, very late first arrival times. And the red one is where the spin is orthogonal, and so the thing is doing this. And because it's doing this, no matter how slowly, as it were, engrossed that it's moving down the waveguide, sometimes the particle will charge ahead, right? And if you just look at the first arrival time at this plane, you'll notice this has a cutoff, this T max, tau max on the diagram. There's actually a longest time before a particle will get to the screen. And after that time, they'll all have gotten there. Their first arrivals will have occurred. And after that, there'll be none. Whereas on the blue, there'll be lots that arrive later. So this is very dramatically different distribution of arrival times. And so you would think, if you can see that, you could tell Bob, just looking at the distribution. So Bob knows that at a certain moment, Alice is going to release a bunch of particles. He doesn't know whether they're going to be spin aligned this way or spin aligned this way. And he can see the arrival times on his side. You might think, well, he should get some information. He should be able to at least make a pretty good guess from the arrival time distribution that he sees, whether they were initially oriented this way or this way in spin. So he would get information about what Alice chose. And this is going to be the key to this. Sorry, I'm going a little bit, I'm almost done. Now, there are complications here because what you can calculate is the first arrival time without a detector there. But of course, for Bob to see it, he has to put a detector in. The detector has to interact with the particle. There's a bunch of physics of that. And some people have thought, well, yes, there is this very different set of distributions without the detector, but those differences will wash out once you put the detector in. Maybe that's right, maybe that's wrong. We would need an analysis to understand if that happens, why it happens. But let's suppose for the moment it doesn't happen. Let's suppose that actually these things are distinguishable. Then we immediately have a scheme for sending superluminal signals. And I'm almost done, but you should be able to understand this. How could I use this to send signals? So here's the scheme. Start with a pair of particles in a singlet state and let them separate, one going off to Alice and one going to Bob. The one will get to Alice a bit before the one gets to Bob. So when this one gets to Alice, the one to Bob is on its way to Bob, but it still has a ways to go. Alice now chooses either to measure its spin orthogonal to or along the direction of the waveguide. And if depending on what she chooses, she can't determine whether it ends up spin up or whether Bob's ends up spin up or spin down. But the normal thought is when she gets a result, as a consequence, Bob's will now definitely have either spin up or spin down in the direction that she chose. And she can choose it either to be along or orthogonal. But if this is right, if she chooses this way, after that point, after she makes her measurement, the distribution will evolve differently than if she makes this choice in ways that Bob could pick up. So if all of that is correct, it's at least the beginnings of a scheme that would allow some amount of superluminal information transfer. Okay, so I've gone a little bit over, but not much. Here's the main reference. If you want to understand where those arrival time distributions calculations came from, here's the reference to this paper by Sidhan and Detlef, published back in 2019. So this is very recent work, and to me, very surprising work. And it suggests either we're going to have a real breakthrough and see this sort of superluminal signaling, or if not, we'll get some much deeper insight coming from somewhere about why it can't be done, even though at first glance it looks like it can. So that's all I have to say. I hope that was of some interest.
Thank you very much, Professor Maudlin. Interesting ideas proposed in your presentation. Dear audiences, if you have any questions, please raise your hand and our organizers make you present. Dear Professor, we have a question written in the bottom. Can you read it?
Well, let me go down to it. Okay, let's see. So the first question is, what would be the nature of the proposed superluminal signal? Does it remain and act as a coherent signal? Well, coherent, I mean, all I'm requiring here for there to be a signal is what Shannon requires for there to be a signal. So the term coherent doesn't really apply at the level of my analysis. All we need is that Bob observes something in his lab. And on the basis of what he observes, so let's say at the beginning, Alice is just going to flip a coin to decide whether she's going to orient her Stern-Gerlach devices this way or this way, right? So initially, Bob has no information about which way it's going to go. The question is just, can he look at the arrival time distribution that he sees in his lab and now make any guess, any amount better than 50-50 about what she did, right? Can he, on the basis of his observations, even mildly bias his guess in the right direction about whether she oriented them this way or that way? That's sufficient for superluminal signaling. Now, to ask whether that's coherent or not, coherent signal, I don't think the concept even applies there. It's just, is Shannon information, right? Does the observable situation in Bob's lab provide any Shannon information about Alice's choice? So it's a very straightforward analysis. I mean, it's much more straightforward than a more sophisticated signal analysis might have to be in other cases. But we're just asking a very basic question of principle here. Second question, is it worthy to assume and study the emitted signal in the space-like region of the light cone? Well, yeah, I mean, this is the whole point, is that if this works, then Alice can, as it were, set her device here, make the decision between whether it's going to be set this way or this way here. And Bob, remember, he's just going to observe the arrival time distribution of the particles coming to him. It's nice to imagine Alice, running 1,000 separate particles at the same time, so he gets a full distribution. He's going to observe that at space-like separation from her choice. And now the question is, does what he see provide him any amount of information about what she did? it's, of course, only makes sense. I mean, we only care about this if it's at space-like separation. Then we get superluminal signaling. So sure, this is exactly what we want to study. It means, as with violations of Bell's inequality, you have to be doing things very fast to really do this. But in a way, I mean, the first question is just whether even these differences in arrival time distributions will get washed out on Bob's side by the kind of apparatus he needs to put in to do the detection. And there are some people who think it will be. They think it must be, for sort of master reasons, which I can't go into here. If that turns out to be true, if the detector washes it out, then there's no point, then there's no point in doing the experiment anyway. If it doesn't, and that should be easier to check, because we don't have to be doing any of this fancy stuff to just see, we create a bunch of particles spin polarized this way, we create a bunch of particles spin polarized this way, we release them from the trap, and then you can just ask, do the arrival time distributions in these two conditions, are they noticeably different? If they are, then I don't see anything that's going to stand in the way of implementing this protocol.
Thank you.
So there's another question. What is the role of consciousness in Bell's experiment? Well, as far as I know, none. The Bell experiments really can be stated without mentioning consciousness at all, if you assume, as Bell does and as I do, that the physical, there's a non-conscious, most of the physical world has no consciousness, tables and chairs and needles on devices and so on, and nonetheless behaves a certain way. So really the Bell issue is about correlations between, say, the settings of some device here and the outcomes, and the outcomes that you get. And you can state those restrictions on the correlations, the Bell's inequality, without mentioning anybody's consciousness. It's just, well, you look at the experiments where the magnets are set this way and this way, you get a certain set of outcomes. And when they're set this way and this way, you get a certain set of outcomes. You would hope that there can just be facts about that, even if there's nobody conscious anymore. I mean, imagine somebody set up an automated lab to run this experiment, and then there was some horrible catastrophe and every conscious being in the universe was eliminated. Nonetheless, you'd think that lab could just chunk along doing this experiment and collecting the data, and it either would or would not violate Bell's inequality.
Professor, can you hear me?
Yes.
So firstly, thanks for your presentation. And actually, my confusion is about a part of your speech that you talked about Maxwell's demon, the failed attempts to physical demons and impossibility of them. But is it then wrong with using a magnetic field for an ionized gas? In Maxwell's demon case as demon, in this case, when we use magnetic field, we can act on an atom differently from another because their difference in speed and their velocity. So it's a way that you can distinguish different particles with their velocity, but anything wrong in it. Can you explain it?
Well, I would have to, again, this is one of these situations where we'd have to work through a proposal in more detail. Of course, you can do something that will have differential effects on atoms with different velocities. As you say, magnetic fields will, because they're going to be deflected to different amounts. In order to do what Maxwell wanted to have done, you have to do more than merely differentially affect differently moving particles. You have to collect together all the faster ones on one side and all the slower ones on the other. And so, of course, the worry is, even if I can do something that will differentially affect particles differently, if the particles are kind of randomly distributed in the directions and velocities of their motions, that the net effect on the entire collective will not create this separation. So certainly a magnetic field will react, will have a differential effect. Whether you could set up a magnetic field with the right structure to use that to sort out the fast ones from the slow ones in the way that Maxwell imagined. I mean, it's not obvious, it's at least not obvious to me how one would do that, because it again, you imagine they're traveling in all different directions and so on, and you're just setting up your field in some way. But if there's a proposal for it, then one of course would have to work through the proposal and see what happens.
But we don't need to collect all of the fast low one in the two parts. What we only need is the average velocity and the average kinetic energy of them. If
Yes.
we make the boundary with a trimagnetic field, there would be only the slow particles can pass this boundary, the other part. So we can put all the gas in initially in one part, and then because of magnetic field, just the slow one can pass through the boundary and go to other part. And with this way, the second part would have less average kinetic energy than the first one.
Well, what you're suggesting is that a magnetic field could basically do what the Maxwell demon does and only emit. I mean, remember, there are a couple things to say here. And again, I can't on the fly give you a detailed analysis of this. In Maxwell's case, of course, it's very important that the demon does no work. All the demon does is open and close doors. And the particles, whatever their speed, just sails through the open door completely unaffected and carries with it all of its kinetic energy. And if the door is closed, it just bounces off the door elastically and keeps all of its kinetic energy, right? So all of its kinetic energy stays on that side. Offhand, if you're talking about using magnetic fields, as you're saying, it doesn't look like the things are going to get through in that way, right? There will be work done. There'll be an interaction with this magnetic field, as far as I can tell, that will be different from the sort of thing Maxwell had in mind. And then you need to take into account what's going to happen with all that. And I can't do it off the top of my head, but at least it is a difference between the example that Maxwell gave and the example that you're suggesting.
Yes, thanks.
Someone has asked, is there any experiment in progress in order to confirm superluminal signaling?
Right. So the answer is, of course, right now, absolutely not. The first step of this is much easier, right? The superluminal signaling part is going to be much more controversial. The first step is just to ask the simpler question: if I have these spin half particles caught in a trap, and I open the trap and let them go down and then have a detector here and try and time the arrival, is there a noticeable difference in the arrival time distributions depending upon whether they've been spin polarized this way or spin polarized that way? That's something that is easily within the ability of contemporary experimental science. This is not something that would be terribly hard to do or terribly expensive to do or need a lot of really specialized apparatus. You want some really, quick clocks to be timing these things, and you need to control your initial state pretty well. But as far as I know, and Sidhan knows more, Sidhan has been in contact with a lot of different experimental groups trying to get people to do these experiments. And it seems as though they can be done. That doesn't mean they will be done, because to do them, you then still need for somebody to decide this is where we want to spend our time and our money for a while. So if that, as I say, if that part, I think the real question is whether you would see this differential distribution of arrival times in that simple case. If you did, then this additional scheme to use it to signal, I kind of don't see how that could go wrong. Maybe it could. Maybe there's something I'm missing. That would be a much harder experiment to do. because now you're talking about doing 2 labs at space-like separation and so on. I mean, it would be very, very hard. But the easier one can be done. It's not yet being done, but we hope that in the next few years, maybe it will be done.
Someone else asked, can the superluminal signaling be computationally simulated by Dirac equation, or we need more?
Well, the actual math that's going into these calculations that Sidhan is doing is the Dirac equation for the wave function, right? For the spinorial wave function. And then the standard guidance equation that you use in a pilot wave theory to give me the trajectories of the particles as a function of the quantum state. So that part, you could, in fact, they do a lot of it just numerically because it's not that easy to solve these things in closed form. But you can do the numerics. In fact, the thing that I showed you from the if I go back to it here, you'll see this histogram that follows the blue curve and the histogram that follows the red curve. I mean, those are histograms because those were just numerical simulations. And in fact, they're coming out sort of as predicted. So yeah, you can computationally simulate this, but notice the simulation is just for the free motion, the motion to get you to the plane. Then there's the additional question of, if I put a detector in, how will that influence the motion of the particles? And that's a very complicated question. Of course, nobody has ever been able to deal with an actual macroscopic detector in detail quantum mechanically. It's just too complicated. So at the point where you have to bring the detector into the picture, there are idealizations or simplifications or so on. And this is where things get rather sticky.
Okay, as the last question, we can get Hossein M. has raised his hand.
Yeah, can you hear me?
Yes.
Yeah.
Yeah, interesting talk, Professor. Well, I wonder what you're mentioning, if it turns out to be true. I mean, the oscillatory behavior of the arrival time distributions for different initial spin states, how does it, in what ways it challenges our intuitive notion of time and causality in quantum mechanics?
Well, the way, what it would show, and I think would actually make observable, if this turned out to be true, it would imply there is a preferred foliation of space-time, which is clearly the easiest way to implement any kind of causal non-locality, right? It may be possible to do it without it, as the relativistic GRW theory suggests, but certainly it's much, 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 much easier to implement causal non-locality if you've got a preferred foliation. If this turned out to be right, it would actually allow you to identify that, to observationally identify it. It would show there was one and actually allow you to pick it out. And that would completely change everybody's picture of space-time in a way that I think is quite a natural way to go, because as I said, as soon as you accept that there's non-locality and you ask yourself, but how do I implement that technically? Putting in a foliation is just, that's the obvious way to go. But the fact that the foliation, you can put it in easily enough, but then often if you think there can't be signaling, as a consequence of that, it's also going to be the case that the foliation, it cannot be observably detected, right? It's got to be there, but you can't, as it were, directly see it. If this turned out to be right, then you could directly see it. And then the game would be over in terms of people trying to just defend a completely relativistic account of space-time.
Okay. Thank you very much for participating in this seminar, Dr. Maudlin, and hope to have you in our future programs. Many thanks for your interesting talk.
Thank you.
Good luck.